Have you ever stopped to think about the invisible force that powers, well, literally everything around us? Your phone, your car, the entire internet, it's all humming along thanks to a surprisingly simple and elegant set of rules. Today, we're going to pull back that curtain and take a look at the world of electric circuits.
You know, it can really feel like magic, but it's not. It is pure engineering. The secret is that it all comes down to just a few fundamental ideas that control how electricity moves, and in the next few minutes, we're going to break them down. By the end of this, you'll see the technology around you in a whole new light. So here's our game plan. We're going to start with the big picture. What even are electric circuits? Then we'll dive into the basic rules that never change. After that, we'll look at how circuits react when you suddenly flip a switch, and then how they handle really complex signals. And finally, we'll see how it all clicks together to make our modern world possible.
All right, let's start with that first step. When we talk about electric circuits, what are we really saying? Well, you can think of it as the fundamental language that all of our modern technology speaks. At its heart, electrical engineering is all about being a translator. It's about taking these big, abstract ideas from physics, things like charge and energy, and using the language of math to build real-world systems that actually do stuff for us. It's where the theory gets its hands dirty.
And the impact of these systems is just massive. We're talking about everything from the power grid that lights our homes, to the supercomputers in our pockets, to the global communication networks that connect us all. And here is the amazing part. Every single one of them is built on the exact same fundamental principles we're about to explore.
Okay, so let's start building that foundation. Before we can get to the wild and crazy stuff, we have to master the basics. The simple, unchanging rules of the road that govern the stable world of direct current, or DC.
So, the first thing we have to get our heads around is voltage. Honestly, the best way to think about it is like water pressure. It's the potential, the push, just waiting to make things happen. If you don't have any voltage, nothing is going to move.
And if voltage is the push, then current is the actual flow. It's the stuff that's actually moving through the wires. So keeping our analogies going, if voltage is the pressure built up in a water tank, then current is the water that's actually gushing out of the pipe.
So you really have to think of them as a team, two sides of the same coin. For anything to happen in a circuit, you absolutely need that pressure, the voltage, to get the flow, the current, moving. You just can't have one without the other.
Now, once we have voltage and current, we get two laws that are just unbreakable. They're called Kirchhoff's laws. The first one is super intuitive. Whatever amount of current goes into a point, the exact same amount has to come out. Nothing just vanishes. The second one says that energy is also conserved. As you trace a path around any closed loop, all the voltage pushes have to be perfectly balanced by all the voltage drops. And why is this so powerful? Because with just these two rules, engineers can figure out exactly what's going to happen in any circuit you can imagine. They're the absolute bedrock of all electrical design.
Okay, so we get the steady, predictable world. But what happens when things aren't steady? The real world is messy. Circuits are turning on and off all the time. So what happens in that split second of change? That's where we get into transients.
I mean, think about it. You flip a light switch. For a tiny fraction of a second, that circuit is in chaos. It's transitioning from off to on. It's not in that calm, steady DC state anymore. So how do we even begin to analyze that moment?
Well, this is where two other superstar components come into play: capacitors and inductors. The absolute best way to think about them is as the circuit's personal shock absorbers. Their whole job is to manage those sudden jolts and smooth things out. And they each have a very specific job. An inductor stores energy in a magnetic field, and because of that, it really hates sudden changes in current. It fights against them. A capacitor, on the other hand, stores energy in an electric field, and it fights against any sudden changes in voltage. This built-in resistance to change is their superpower. And you can see their effect perfectly right here in this table. When a change happens, things don't just snap to their new state instantly. They sort of ease into it. They decay over time. See how after just one of these time constants, the voltage is already dropped by a lot? By the time you get to 5 time constants, the show's over and the circuit has settled into its new normal.
And if you're thinking, okay, that's kind of neat, but what's the point? Well, have you ever used the flash on a camera? This is exactly what's happening. A capacitor slowly stores up a ton of energy, and then in a fraction of a second, bam! It discharges all of it. That's a transient response right there in your hand. So we've got the steady state, and we've got the moment of change. But what about signals that are always changing? I'm talking about the AC power in your wall or a Wi-Fi signal flying through the air. This brings us to our third and final pillar, frequency response.
For these constantly changing signals, we need a new concept called impedance. You can think of it as resistance for AC circuits, but it has a really cool trick up its sleeve. Its value actually changes depending on how fast the signal is wiggling up and down.
And this is where we see the secret lives of our components. A resistor? It couldn't care less about frequency. Its opposition is always the same. But inductors and capacitors, oh, they are dynamic. They behave in completely opposite ways depending on the signal. At low frequencies, an inductor lets everything pass, but at high frequencies, it blocks it. A capacitor does the exact opposite. This simple difference is basically the key to all modern electronics.
And this behavior is incredibly useful because it means we can build filters. By mixing and matching these parts, we can create a circuit that acts like a bouncer for frequencies. We can build a low-pass filter that only lets the bass through, or a high-pass filter that only lets the treble through. This is the absolute foundation of signal processing.
Okay, that was a lot, I know. So let's take a quick step back and see how these three big ideas, the steady state, the transients, and the frequency response, all fit together. See, to really understand any circuit, you need all three perspectives. You need the foundational laws of DC to know how it behaves when things are stable. You need transient analysis to know what happens in that instant of change, and you need frequency analysis to predict how it will handle the complex, messy, oscillating signals of the real world.
And this, right here, is the key takeaway. You look at something incredibly complex, like a smartphone. It's a power system, a computer, a control system, and a radio transmitter all packed into one tiny device. And every single part of it, from the battery to the antenna, is designed using the exact same principles we just talked about.
From the very first telegraph lines, all the way to the quantum computers that are being built today, these same fundamental rules have been the toolkit for every single innovation. They are timeless, they are the language we use to turn ideas into reality. The only question left is, what are we going to build with them next?